Okay, so we said that heavy things can actually be supported by surface tension, and we're going to look at an example of that. And actually, normally at this point in time, I would do a demonstration where I'd show that that the surface tension of water can indeed support a paperclip, provided you um, apply it gently. But we can actually mathematically prove that it should be possible to do as well, just by considering the forces at a given point on the paperclip. And there's quite a few approximations in here, but basically what we can do is we can basically say if the paperclip is going to float, then essentially the force due to its weight needs to be counteracted by the force due to surface tension added to the force due to buoyancy, right? So that's really the question. Will the paperclip float on water? So we've just said this, that basically the force due to the interfacial tension plus the force due to the buoyancy is greater, it has to be greater or equal than the weight in order for the paper to float, okay? And incidentally, this is the same, this equation here that we've written here is the same as just literally considering the balance of the forces, because both sides are multiplied by 1 over h. So for example, you could rewrite that equation as 1 over h multiplied by fit plus fb is greater than or equal to 1 over h f weight. And we could then just cancel the 1 over h's. All right, so therefore we can kind of put all those equations together. So we've got this one and that goes to there. So this is our fit over h. This one is our FB over H, and this one is obviously our FW over H. And sorry about the lines, they keep on coming and I don't know why. Okay, if we then work out and put the numbers in, we end up with 2 times this over that, plus here we've got basically r squared, so this is r squared here, and then we're timesing it by the density of water, which is 1,000, and the gravity, which is that. So that ends up being 10,000 times by pi. And likewise here, we've got the density of the paperclip, which is 8,000, and we've got gravity, which is 10. So again, we've got 80,000 there. Again, pi, and again, the radius squared. So, you put all this together, you end up with 0.014 over root 2 should be bigger than this value here, okay? And you can put this into your calculator and double check that this is the case by yourself. 0.014 divided by root 2 is roughly equal to 0.1 because root 2 is that's 1.4 roughly, okay? And this whole term ends up being roughly equal to, well, this whole term equals 0.05, and so therefore this one is bigger than this one, and so therefore this is okay. So it should float, okay? And I'll try to find a video that shows a paperclip being floated, and if not, I'll try and find at least some pictures of that occurring, okay, and post them in the module folder. Okay, so what happens when we introduce surfactants? Okay, so this is our air-water interfacial tension of for air and water, and what happens when we add surfactants is this: it goes down. Okay, so that's a key point. Adding surfactant reduces the air-water surface tension, and the result. And as this has been part of the demonstration, I'd have just dropped a tiny drop of surfactant molecules, just basically fairy liquid, into the pure water plus paperclip solution, away from the paperclip, and you would be able to see that the paperclip sank. Okay. The key point here is that this is what the surfactants are doing. They're reducing that surface tension, okay? And they're reducing it almost to the point where you have an air organic solvent surface tension, okay? And this maybe isn't surprising if you think about what actually is happening. If you've got your oriented monolayer of surfactants, sitting here, and I'll use that line and make it a longer one. If you've got your oriented monolayer of surfactants like this, then the air basically sees a whole bunch of organic chains. Okay, so the air molecules up here, I'll just go and get the laser pointer. The air molecules up in air in here are essentially experiencing, when they come down here, they're experiencing an organic environment, and so therefore the surface tension being similar to that of an organic solvent isn't particularly surprising. Okay, however, it obviously isn't quite as low as air, liquid, hydrogen. That again shouldn't be surprising because these two things are basically miscible. The key point here is that surfactants can therefore be used to change that interfacial property. Okay, and one of the things you can do with that is you can use surfactants to stabilize colloidal dispersions. For example, you can use surfactants to change the oil water interfacial tension. So, this is straight oil water and the value is here, so it's slightly lower than it should be. It's about 50 odd. Okay, it's basically, well, it's 50 odd or 40 odd. All right. If you put surfactants in, that changes and we get sort of to the 1s or 10s, so it significantly drops, and that makes this emulsion much easier to stabilize, because if you remember, if we want to make an emulsion, we still have to put some work in. So, if you want to make an emulsion, in an emulsion, delta A is bigger. So we need a smaller that. Or you could look at it the other way and say, if your surface tension decreases, you're able to support a bigger area of interface. And likewise, if you have a microemulsion, then this is a thermodynamically stable. Dynamically stable. Microemulsions are thermodynamically stable. In this case, the surfactant is reducing the interfacial tension significantly. And again, now you have a much greater interfacial area. And this is why microemulsion droplets are of the region of sort of maybe 4 nanometers. Oil water emulsion droplets are maybe about 1 micrometer, maybe a bit bigger. Okay, and so this has still got quite a large, got a relatively small surface area, whereas when you have a much smaller particles, you get an even bigger surface area. Okay. But the key point really is that surfactants reduce the air-water interfacial tension, and because of that, they have a lot of important properties surrounding the ability to stabilize emulsions, of course, with lots of uses in food and in the industry, etc., and cleaning. But also they can do some pretty interesting other things. So microemulsions, for example, can be used for drug delivery. So why does this actually happen? Well, the key point about a surfactant is that it's an amphiphile. And that means it basically likes both environments. Okay? And there's several ways of kind of seeing this process occur, but basically, because you have an amphiphile, you have a tendency for that surfactant molecule to want to absorb at that air-water interface. And the reason that the surface tension reduces is because there's now an arrow taking molecules towards the interface. So the surface pressure, and pressure is basically the push towards a position, right? The pressure is increased. So surfactants want to move towards the interface to make this kind of oriented monolayer, and that motion, that wish to move, increases this surface pressure, which reduces the surface tension. Okay. And you've got an equation for that. So pi here is the surface pressure. This is the surface tension of the pure interface, and this is the new surface tension after you've got surfactant added, basically. Okay, so if you've got a pristine surface pressure, a pristine interface, so just air and water, then you have a surface pressure equal to 0, and therefore this is the same as this. Okay, but why is it that actually surfactants want to absorb at the interface? We've said that they want to absorb, we've talked about the result of it, but we haven't really talked about the chemistry surrounding it. Now, we know that the chemistry is basically dictated, whether something's going to happen or not, is basically dictated by Gibbs free energy. Okay, that's what's going to say whether something's going to spontaneously occur or not. Now, that Gibbs free energy, we also know, is can be made up of contributions from enthalpy terms and also entropic terms. Okay, so let's think about what actually happens by the process of surfactants absorbing at the interface. Right, if you think about an interfacial layer, we have a situation where, you have everything coming closer. So what happens in terms of the enthalpy? Right, well, at the interface, you have still got hydrogen bonds between the water and the head groups. That's, you obviously have some new hydrogen bonds between maybe nearing head groups, for example, particularly if you've got non-ionic surfactants. But basically, those hydrogen bonds are going to be pretty similar compared to, if you just had surfactants sitting around in the water layer down here, okay, which is obviously not drawn. So this is roughly the same. You've got some new attractive interactions. You're going to have attractive interactions between the tails because they're suddenly going to be getting closer together. And so now we have some attractive and some favorable bonding interactions between the tails. Okay, now these are going to be mainly, because these are alkyl tails typically, these are going to be mainly van der Waals forces. We know that van der Waals forces, or instantaneous dipole forces, London dispersion forces, whatever you prefer to call them. And we know that these are relatively small, say, for example, compared to hydrogen bonding. So, while this will give us a negative delta H, it will give us a sort of a favorable interaction. It's probably going to be quite a small favorable interaction. On the other hand, of course, if we've got charged head groups here, 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 and they're all sort of positively charged, then they're going to repel each other. Okay, so they're repulsive interactions, and they're going to be unfavorable with a positive delta H. So I think what we conclude on the basis of enthalpy, at least, is that if it is going to have be a favorable interaction leading to a negative delta G, it's going to be a small contribution. And if you have a cationic or just generally an ionic surfactant, it may well actually be a positive contribution. So how does delta G become negative? Well, I mean, if it's not due to this, if this is either small and negative or just generally small, and even if it's positive, then really what has to be is this bit here, the minus T delta S. But that's a little bit odd, isn't it? Because what are we making? We're making an ordered oriented monolayer. How on earth can we get an increase in entropy from that process? But that's what's got to be the case, because this, once again, this is small, might even be positive. We know that delta G is negative because we know that they do absorb at the interface, so therefore the reason has to be due to entropy. And the reason we've got to talk about this is we've got to think, instead of thinking about this question from the surfactant's point of view, because obviously each surfactant molecule will essentially see an increase in order through the process of absorbing at the air-water interface. We need to think about it from the solvent's point of view. And in this case, the solvent is water. Now, water we know a lot about, okay? We know that water without any surfactant bonds very strongly to itself to form hydrogen bonds, and that's one reason, for example, why water, has the properties that it does. Okay, it's also one of the reasons why water has a very high interfacial air-water interface, interfacial tension. It's because of the strength of the hydrogen bonds. Okay, what happens when you put a surfactant in water? Well, the head group's fine because that's kind of the purpose of a surfactant. It's got a head group that is hydrophilic. That's going to form hydrogen bonds with the water, whether it be charged or whether it be non-ionic with lots of hydrogen bonding groups. But the surfactant also has a tail, which is hydrophobic. Now, around that tail, you then have water molecules. Of course, you've got to have water molecules because we can't make a vacuum. But around that tail, these water molecules are going to be effectively experiencing their own interface with a hydrophobic moiety, okay? And within this area, then you have the same kind of structure as you do at the air-water interface. You have a structure, a crystallization of the water around it. You can call it a clathoric cage if you like. You know, if you think about the enzymes part of this module, we called it a clathoric cage there. But in this case, we can call it a hydrophobic cavity. You know, and basically that hydrophobic cavity causes the water molecules to be forced into a more ordered or more crystalline state. And of course, every single time you have one surfactant molecule, you are imposing order on multiple water molecules. Okay. So if you take this alkyl chain and you take it away from the contact with water by aligning it at the air-water interface and taking it away from the water, then you relax this crystalline state of the water molecules around it. Now, this relaxation, this reduction in entropy, this gain in entropy, sorry, this reduction in crystallinity leads to a massive gain in entropy because you've lost all this order, and that is really the driving force for surfactants to order themselves at the air-water interface. And this driving force is known as the hydrophobic effect. Okay, and as I said, as I also said in the enzymes lectures, I mean, you can describe the hydrophobic effect in a number of different ways, but they all come down to basically an ordering of water molecules that is being relaxed. Okay, and therefore that means that the surfactant will tend to organize at the air-water interface. So, sort of just to summarize that, we have surfactant molecules that will absorb at the air-water interface. Of course, the action of that increases the surface pressure, and we get our oriented monolayer and the surface tension reduced. And because the surface tension is reduced, and because of the equation W is equal to gamma times by the amount of area, basically this is staying the same. This is the same. This is less. And so therefore the work required is less. And that is basically why, this tends to actually happen. Okay. And this is why the surfactants can then stabilize droplets and bubbles. Okay, so just a quick little question. It's quite a straightforward question. I'd like you to pause the recording here and have a quick think. Okay, we're back. So hopefully you had a little think about this. Basically, it says the addition of a small quantity of STS, sodium didecyl sulfate, at a temperature, which actually doesn't really matter for this question, is observed to decrease the surface tension of water by a certain amount. We need to then calculate the change in surface pressure. Does it increase or decrease? Well, the surface pressure has to increase. So surface pressure goes up. And that's because we've added surfactant. Which is going to tend to absorb. And I write into air-water interface as A/WIF, by the way. Okay, that's air-water interface. It's quite a good piece of shorthand. So of course the surface pressure has to increase, but how much does it increase by? Well, we can use the equation. Pi is equal to that gamma 0. So this is the surface tension of the pure air-water interface minus pi. The new surface tension of the interface. Now we don't have the new surface tension of the interface, but we do have the decrease. So what we can say is the decrease is basically this number. The decrease is basically this. Okay, so you can work out what the new surface tension is. We can say, well, that is equal to 72 minus 15 millinewtons per meter, which is equal to what's 57, isn't it? Millinewtons per meter. Or we can just say, well, it's changed by 15, so it's equal to 15 millinewtons per meter. Okay, so it's a pretty straightforward question in terms of getting a number, but I really want you to understand the point about surface pressure too. Okay. Okay, all of this comes down to numbers that I've been giving you. Okay, so we've been saying, oh, it decreases by this. I've said that the oriented monolayer has a surface tension of about 30 millinewtons per meter. I've said that the air-water interface has a surface tension of 72 millinewtons per meter. How do we know? And there are multiple ways of measuring surface tension, but generally what they involve is basically you applying a force to the air-water interface in one way or another. So in this case, what you've got is you've got a ring of metal, and you're basically just going to use a force to pull it up, okay? And we measure how much we have to pull this string in order to break that interface. So you'd essentially, what you'd see is you'd see an increase in force, and then suddenly no force anymore. And that maximum force there is going to basically be, so you can essentially put a force applied versus distance. And this force here is basically going to tell us essentially, this is going to be very much related to the surface tension, isn't it, once you've calibrated your ring. Likewise, you've got the same thing here. You've got a plate being pulled out of water. Okay, so once again, we've got a plate being pulled out of water. We've got a force that's counteracting, that's being used to pull that plate out. The surface tension is counteracting that force, and we measure the force we apply until we see no force required to apply anymore. Okay, so once again, from that we can get what the surface tension is. Finally, we can actually look at we can do pendant drop measurements. So this is basically the force due to gravity, and you can either look at the shape of the drop, or you can actually just measure what the volume of the drop is, and that will tell you what the surface tension is. Okay, and there are other methods too, but basically with these methods we can get a graph of surface tension versus concentration of surfactant. Okay, and this graph follows this general trend. Okay, so we basically have a logarithmic trend. Well, we have a trend that is shown like this on a logarithmic scale. Okay, so this is a log-lin scale, actually, just to be very, very clear on that one. And it generally obeys this equation here, which I'm not ever going to get you to use. But this equation here explains why it is that typically we plot surface tension as a function of log of the concentration of surfactant. And that's a really key point, really, because if you just plotted it as a function of the concentration of surfactant, you'd need to have a very, very long axis scale in order to see this behavior. And obviously this behavior occurs over lots of orders of magnitude. So behavior occurs over several orders of magnitude. So for example, for SDS, I've given you this position here, which is around about sort of 8 millimolar. But this position here could well be, 10 to the minus 6 molar, for example, or micromolar. So this covered here is many orders of magnitude. Typical point, what we see is we start with an air-water interface. As our surfactant absorbs, this air-water, the surface tension starts to go down, and we reach this point here, which is the break point. This break point is known as the CMC. And basically what we're going to say is we're going to explain what's actually going on here in the next slide. Okay, so this is something that I'll often ask you in questions. I have often asked in the past. So basically what we can see here is we can basically see we've got this at these various points. So we've got position A, position B, C, etc. And so all the way up to A, what we have is we have soluble surfactants. So this would be surfactant is soluble. Oh my goodness, that's awful. Can I raise that? Let's try writing that again. So this is surfactant is soluble. Okay, and in other words, we haven't got um, any surfactants absorbing at the air-water interface because basically there's not enough surfactant in there yet in order for the driving force due to entropy to actually push the surfactant molecules to absorb. As we move away from position A, we start to see a reduction in the air-water interface. So this would be sort of 72 or indeed 70 millinewtons per meter. The reason I've got 70 on the previous slide is that, 72 is for a perfectly pure sample of water. 70 is for, your normal water that you get industrially. Okay. Anyway, as we move away from A, we can see that the surface tension is decreasing, and because the surface tension is decreasing, we therefore know that we've got surfactant that's absorbing. Now, initially, you're just going to get a few molecules absorbing, but as we move down this curve, we're going to see more and more water molecule, more and more surfactant molecules absorbing at that interface until we get to around about B. And at about B, we've got an interface that's nearly full. Okay, so this would be the state here at B. We've got an interface that's nearly full, and between B and C, we start to get what is a linear area here, quite close to C, and that's where the interface is full, but we're still able to add a few more surfactant molecules into that interface, by basically reconfiguration of the packing. Okay, and then from C onwards, we get this breakpoint at C, and then from C onwards, what we see is we start seeing another phase forming, and that phase is called micelles. Okay, and at that point in time, we only see a slight reduction or indeed no reduction at all in surface tension, because after there, we can basically assume that that interface, to all intents and purposes, is full and doesn't change anymore. So key point to note throughout this entire thing is that we've always got surfactant in the bulk as monomer form, okay? And this surfactant here in the bulk is in equilibrium with the surfactant that's at the interface. So there's going to be a constant exchange process between these two. And likewise, there's going to be a constant exchange process between the surfactants as monomers, surfactants in these micelles, and the surfactants at the air-water interface. So there's multiple equilibrium processes set up. So I'm just going to write that in pen. So we've got essentially an equilibrium process here. And we've got an equilibrium process here. And we've got an equilibrium process here. Sorry, oh, goodness. And we've got an equilibrium process here.